1855, at a lavish state dinner hosted by Napoleon the Third of France, the most honored guests at the table were handed cutlery made from a strange, lightweight, silvery metal. The less important guests, seated further down the table, had to settle for something far more ordinary, gold and silver. That silvery metal reserved for royalty and heads of state was aluminum, and at the time, it was worth more per gram than gold itself. 3 decades later, in 1884, when Americans wanted to cap the newly completed Washington Monument with a symbol of extraordinary technological achievement and wealth, they chose that same metal, a 6-pound pyramid of pure aluminum placed at the very top of the tallest structure in the world. Today, that identical metal sits crumpled in your kitchen drawer as disposable foil, or crushed flat in a recycling bin as a soda can worth roughly 1 cent in scrap value. This is the story of how one of the most common elements on the entire planet became, briefly, one of the rarest and most valuable substances human beings had ever touched, and how it collapsed, just as fast, into something so cheap we throw it away without a second thought. To understand how something could swing this wildly in value, you have to start with a genuinely strange fact about the Earth itself. Aluminum is the 3rd most abundant element in the entire crust of our planet, and it is by far the most abundant metal, making up roughly 8% of everything beneath your feet. That number is almost impossible to reconcile with how rare and precious aluminum once was. Iron, copper, gold, silver, tin, all of these metals had been mined, smelted, and worked by human civilizations for thousands of years before anyone had ever held a single piece of pure aluminum in their hand. The reason for that gap is not scarcity, it is chemistry. Aluminum never occurs naturally as a pure metal anywhere on Earth. It is always locked inside compounds, bonded tightly to oxygen and other elements within rock and clay, most commonly in a mineral called bauxite. That bond between aluminum and oxygen is extraordinarily strong, far stronger than the bonds holding other common metals inside their ores. Ancient civilizations could smelt iron using nothing more sophisticated than a charcoal fire and a forced draft of air, because the chemical bond holding iron inside its ore is comparatively weak and breaks apart under moderate heat. Aluminum's bond simply refuses to break that easily. You can heat bauxite in a fire for as long as you like, and it will sit there completely unchanged, the aluminum trapped inside as securely as if it were locked in a vault with no key in existence. For most of human history, that vault stayed sealed. Aluminum was quite literally invisible and unreachable, hiding inside common dirt and clay across every continent on Earth, while human beings mined comparatively rare metals like gold and silver, simply because those metals were willing to give themselves up to primitive extraction methods. The first person to isolate even a tiny impure sample of aluminum metal was a Danish chemist named Hans Christian Ørsted, working in 1825. His method was painstaking, expensive, and produced only minuscule quantities of the metal, contaminated with impurities. A few years later, in 1845, a German chemist named Friedrich Wöhler refined the process and managed to produce small pellets of aluminum pure enough to study properly. But these were laboratory curiosities, not industrial materials. Producing even a single ounce of aluminum through these early chemical methods required enormous amounts of labor, dangerous reagents, and considerable expense, which is exactly why the metal commanded such an extraordinary price once it started appearing in European high society. By the 1850s and 60s, a French chemist named Henri Saint-Clair Deville had improved the extraction process enough to produce aluminum on a slightly larger scale. And this is the era when Napoleon the Third began commissioning aluminum items specifically to demonstrate imperial wealth and scientific sophistication. Aluminum jewelry, aluminum decorative objects, and yes, aluminum cutlery for the emperor's most distinguished guests all became status symbols precisely because the metal was so fantastically difficult to produce. At certain points during this period, aluminum sold for a price comparable to silver, and in some cases exceeded the price of gold entirely, making it one of the most expensive substances a wealthy person could own. This scarcity is also why the Washington Monument received its famous aluminum cap in 1884. The monument's engineers wanted a material for the pyramidal tip that would resist corrosion, reflect lightning safely, and symbolize the cutting edge of American industrial capability. Aluminum checked every box, and at 6 pounds, that small cap represented a substantial financial investment, roughly equivalent to the daily wage of a skilled laborer multiplied many times over. Newspapers at the time marveled at the idea that the tallest monument in the world was crowned with a metal so rare and so difficult to produce that most Americans had never seen it in their entire lives. The world, at this point, desperately wanted more aluminum. Industrialists could already see its potential: lightweight, strong, resistant to rust, useful for everything from cookware to construction. The demand existed. The applications existed. What did not exist was an affordable way to actually get the metal out of the rock it was trapped inside. That changed almost overnight in 1886 through one of the most remarkable coincidences in the entire history of industrial chemistry. On opposite sides of the Atlantic Ocean, two young men working entirely independently of one another, with no knowledge of each other's research, solved the exact same problem within months of each other. In the United States, a 22-year-old chemistry student named Charles Martin Hall, working in a makeshift laboratory in his family's woodshed in Ohio, discovered that dissolving aluminum oxide in molten cryolite and then running an electric current through the mixture would cause pure aluminum to separate out and collect at the bottom of the vessel. Around that exact same time in France, a young metallurgist named Hall-Héroult, working independently and unaware of Hall's research on another continent, arrived at essentially the identical solution using essentially the identical electrochemical principle. Neither man had copied the other. Neither man had even heard of the other's work at the time of his discovery. Two minds, separated by an entire ocean, cracked open the exact same vault using the exact same key within the same calendar year. This process, which came to be known as the Hall-Héroult process, remains, with only modest refinements, the primary method used to produce aluminum anywhere on Earth to this very day. It works by using massive amounts of electrical current to break the powerful chemical bond between aluminum and oxygen, a bond that no amount of ordinary heat could ever break, but that electricity applied in sufficient quantity could split apart with remarkable efficiency. The moment this process became commercially viable, the price of aluminum did not simply decline. It collapsed. In the space of roughly 10 years following the discovery, the price of aluminum dropped by more than 90%. A metal that had once been reserved for emperors and monuments suddenly became affordable enough for ordinary industrial use, and both Hall and Héroult understood immediately what they were sitting on. Charles Martin Hall moved quickly to secure a patent on his process in the United States, and he partnered with a group of investors in Pittsburgh to found a company that would eventually become the Aluminum Company of America, known today simply as Alcoa. Hall-Héroult, on the French side of the Atlantic, similarly moved to protect his discovery, and the company built around his patent eventually grew into Pechiney, which remains one of the dominant aluminum producers in France and Europe to this day. Both men, in essence, had discovered the same door into the same vault, and both immediately built companies designed to control everything that came out of it. For decades afterward, Alcoa held an absolute, airtight monopoly over the American aluminum industry, and Pechiney held a comparably dominant position across much of Europe. Anyone who wanted to buy aluminum in the United States had exactly one company to buy it from, and that company controlled every stage of production, from the mines that extracted bauxite ore to the smelters that ran the Hall-Héroult process to the mills that rolled the finished metal into sheets. There was no competition because Alcoa had systematically acquired or blocked access to nearly every viable source of bauxite ore, every patent related to the smelting process, and every hydroelectric power source large enough to run an aluminum smelter at industrial scale. This was not a company operating within a competitive market. This was a company that effectively was the market. For a long time, the United States government tolerated this arrangement, largely because aluminum remained a relatively minor industrial material through the early decades of the 20th century, useful for cookware, some construction applications, and various consumer goods, but not yet essential to national security in any dramatic way. That calculation changed completely with the outbreak of the Second World War. Aluminum, it turned out, was the single most critical material for building military aircraft. Its combination of lightweight and structural strength made it irreplaceable for airplane frames, and the United States found itself needing to build an air force capable of fighting a two-front global war almost from scratch. Aircraft production during the war years reached staggering numbers, with the United States eventually manufacturing well over 200,000 military aircraft, each one requiring enormous quantities of aluminum sheet, aluminum rivets, and aluminum structural components. And every single ounce of that aluminum, without exception, had to come from one company, because Alcoa still controlled essentially the entire domestic supply chain. This created an extraordinarily uncomfortable situation for the federal government. The nation's entire capacity to build the aircraft needed to win a world war depended entirely on the production decisions, the pricing, and the operational capacity of a single private corporation. If Alcoa could not scale production fast enough or chose not to, there was no alternative domestic supplier the government could turn to instead. The government responded during the war by essentially forcing Alcoa to license its technology to other companies and by funding the construction of additional smelting capacity through wartime programs, effectively creating temporary competitors almost by government decree, because the alternative was simply unacceptable from a national security standpoint. But this wartime arrangement was a stopgap, not a permanent fix. And once the war ended, the fundamental legal question remained completely unresolved. Should one company be allowed to control an entire strategic industry indefinitely? That question finally reached a definitive answer in 1945, in one of the most significant antitrust rulings in the entire history of American business law. A federal appeals court in a case known as United States versus Aluminum Company of America ruled decisively against Alcoa, finding that the company had illegally maintained a monopoly over the aluminum industry, not necessarily through predatory or fraudulent behavior in every instance, but simply through the systematic, deliberate exclusion of any and all competitors from ever gaining a meaningful foothold in the market. The court's reasoning was genuinely groundbreaking. It established that a company could be found guilty of illegal monopolization even without proving that it had engaged in specific acts of fraud or coercion against its rivals, simply and deliberately maintaining a market share so dominant that no competitor could realistically emerge was, on its own, sufficient grounds for an antitrust violation. This ruling reshaped American antitrust law for decades afterward and forced the government to actively dismantle pieces of Alcoa's dominance, opening the door for the wartime competitors that had emerged under government pressure to remain permanently in the market as legitimate, independent aluminum producers. The monopoly that Charles Martin Hall had built from a discovery made in his family's woodshed had grown so powerful that it took a literal act of the federal judiciary to break it apart. For several decades following that ruling, the aluminum industry in the United States and much of the Western world settled into a more conventional competitive structure, with several major producers operating alongside one another, prices set by genuine market competition rather than monopoly control, and production spread across numerous smelters in numerous countries. Aluminum, once the exclusive province of emperors and government monopolies, became genuinely ordinary, showing up in kitchen foil, in soda cans, in the frames of bicycles and eventually automobiles, in the siding of houses, and in the fuselages of the commercial airliners that were rapidly transforming global travel. The metal that had once required a specialized chemical laboratory and enormous expense to produce even in tiny quantities was now manufactured by the millions of tons annually, cheap enough that entire industries were built around the assumption that it would simply always be available, always be affordable, and always be somewhere else's problem to worry about. But underneath that apparent normalcy, a new and very different kind of concentration was quietly building, one rooted not in patents or corporate monopoly, but in the sheer physical demands of the production process itself. Remember that the Hall-Héroult process works by forcing an enormous electrical current through molten material to break apart an exceptionally stubborn chemical bond. That single fact, more than any other, has determined where aluminum gets made throughout the entire history of the modern industry. Producing aluminum requires staggering quantities of electricity, far more than almost any other major industrial process on Earth. Today, aluminum smelting alone consumes roughly 3.5% of all the electricity generated across the entire planet. A figure that becomes even more remarkable when you consider that aluminum represents only a small fraction of total global industrial output by value. Smelters, as a direct consequence of this electricity dependence, have always clustered around the cheapest available sources of power, wherever those happen to be located in any given era. For much of the 20th century, that meant aluminum production clustered around massive hydroelectric dam projects, places like the Pacific Northwest of the United States, parts of Canada and Norway, regions blessed with abundant, cheap, renewable electricity generated by fast-flowing rivers. But over the past 3 decades, the center of gravity for global aluminum production has shifted dramatically and almost entirely toward a single country. China now produces roughly 57% of all the aluminum manufactured anywhere on the planet, a level of concentration in a single nation that dwarfs even what Alcoa achieved at the height of its American monopoly decades earlier. This concentration did not happen by accident. China built enormous coal-fired power plants specifically to feed a rapidly expanding network of aluminum smelters, offering electricity prices low enough to undercut producers almost anywhere else in the world, while simultaneously investing heavily in the mining and processing infrastructure needed to secure bauxite supplies from countries across Africa, Australia, and Southeast Asia. The practical consequence of this shift touches nearly every piece of advanced technology manufactured anywhere in the world today. Every Tesla built with an aluminum vehicle frame, every iPhone housed in its distinctive machined aluminum casing, every commercial airplane fuselage assembled from aluminum sheet and structural components. The raw metal at the foundation of all of these products has an extremely high likelihood of having passed, at some stage of its production, through a Chinese smelter, many of which operate under significant influence or direct control from state-owned enterprises and government industrial policy. This represents a genuinely different kind of concentration risk than the one American regulators confronted with Alcoa in 1945. That earlier monopoly was a domestic corporation subject to domestic antitrust law, and a domestic court could order it broken apart, which is exactly what happened. Today's concentration is international, rooted in one nation's decades-long industrial strategy and its command over cheap electricity generation. At a scale most other countries simply cannot replicate without similarly enormous, centrally coordinated investment in power infrastructure. There is no equivalent court with the authority to order that kind of restructuring, and no simple legal remedy waiting in the wings the way there was in 1945. Governments in the United States, across Europe, and elsewhere have taken notice of this dependency, and in recent years have begun exploring tariffs, domestic smelter investment, and efforts to diversify aluminum supply chains away from reliance on any single country. But rebuilding domestic smelting capacity is an extraordinarily expensive, electricity-intensive undertaking that takes years to plan and years more to construct. And it requires exactly the kind of cheap, abundant, reliable electricity that made China's rise in this industry possible in the first place. The fundamental physics of aluminum production has not changed one bit since Charles Martin Hall first ran an electric current through molten cryolite in his family's woodshed back in 1886. Breaking that stubborn bond between aluminum and oxygen still requires enormous amounts of electrical power, and whoever controls the cheapest, most abundant supply of that power will always hold an enormous structural advantage in producing this metal, regardless of what patents exist, what companies are involved, or what antitrust courts might eventually rule. Aluminum's entire story, from a metal so rare that an emperor gave it to his most honored dinner guests, to a substance so common that we crumple it into a ball and throw it in the trash without a second thought, comes down to one single persistent problem and successive solutions to that same problem across nearly 2 centuries. The metal was always there, locked inside common rock scattered across every continent on the planet, waiting for someone to find a way to break it free. Early chemists found an expensive, laborious way to break it free, and the result was a metal briefly more valuable than gold. Hall and Héroult found a cheap electrical way to break it free, and the result was a metal so abundant it reshaped modern manufacturing entirely. And today, the question of who controls the cheap electricity needed to keep breaking it free at industrial scale has become one of the quietest, least discussed, and most consequential questions in the entire global economy, sitting invisibly behind every airplane, every smartphone, and every electric vehicle rolling off an assembly line anywhere in the world.